right, the last part of vectors, part 4, is vectors in space. Okay, so space means like a 3D type of coordinate system. So everything that we've done up until now has been in what we call the XY plane. Okay, in that diagram, the XY plane is like the bottom. Everything we've drawn has been, vectors in that area. Now what we're going to be doing is coming up off of that. Because we're doing 3D, when I describe direction, I can't really say up, down, left, and right anymore. Okay, that gets a little confusing. So when I have to describe the direction of a vector, I'll describe it in the direction of the axis. So when we talk about unit vectors now, I'll say that I points in the direction of the positive x-axis, j points in the direction of the positive y-axis, and k, our new unit vector, is the one that's going to be coming up off the plane. So think if you had like a table, the z-axis is coming up from it. That's the 3D part. This type of coordinate system, okay, our book refers to as a right-handed coordinate system. And the way you can remember which axis points in which direction is your index finger always would point in the direction of the positive x-axis, middle finger would point in the direction of the positive y, and your thumb would point in the direction of the positive z. So all three axes are perpendicular to each other, and that tells you which way they point. If you do it with your left hand, and you line up the x and the y, like that, what happens is the z's point in opposite directions. So down instead of up. So the coordinate system we use is referred to as a right-handed coordinate system. So any question on the idea of the coordinate system? Which axis points in which direction? Yeah?
Why is the positive x-axis pointing down?
So the positive x-axis, if you think of it as like if this book was the coordinate plane, the x-axis is this side. The y-axis is this side. And then the z-axis is coming up out of the book. So it's not that the x-axis is going down. It's going like on that side. It's, if you look at it, it's with perspective. Yeah. So the x-axis is like the short side of the book here, the y-axis is the long side, and the z-axis would be coming out of it. Right? Yeah. We don't really do a ton of sketching in 3D because you can do the same things we've done. Like you can take two vectors in 3D and then connect them together and draw the third one. But adding in 3D visually is kind of hard just because drawing it is hard. So we're going to stick to more numerical kinds of things in 3D. All right, the first thing we're going to look at is how we find the distance between 2 points in 3D. All right. So what I want to try to look at is like finding E. E is the distance from the back left on the bottom of the box to the front right top corner of the box. So it's the distance across that diagonal inside the box. Okay, to figure that out, we're going to have to find something else. Okay, A, B, and D would be given to you. That's the length, the width, and the height of the box. If you knew that A, the B, and the D, does anybody have a guess what else you're going to have to find first before you can try to find E? So remember, E is the distance from the back left bottom to the front right top corner of the box. But you're going to have to find something before E. Yeah?
You're going to have to find C.
You're going to have to find C. Right? So you're going to be able to make a triangle in the box that's going to be a right triangle. But the only way to do it to find E is if you know C. Okay. How can we get C, which is the distance across the diagonal of just the bottom of the box? So if you were looking at this book, this was the bottom of the box. A is one side, B is the other. How would I get the distance across the diagonal?
Pythagorean theorem.
Yeah, we could use Pythagorean theorem. Right? And it would just be a squared plus b squared equals c squared. Okay. So that's just Pythagorean theorem on the bottom of the box. Now, if I wanted to find E, what sides would be involved if you were going to make another triangle to find E? And this is going to be like a triangle that's kind of standing up in the box now. It's not going to be laying flat like the A and the B, C was. It's going to be standing up. Yep?
C squared plus D squared.
Yeah, we would need the C, the D, and the E. And those would make another triangle. Right? So C squared plus D squared equals E squared. That's another right triangle inside the box. It's not flat like it's laying down. It's like it's coming up like that now in the box. And you're making a triangle. So now with these two formulas, we can substitute one into the other, and that'll give us a formula for E squared. Okay. C squared is A squared plus B squared. Well, E squared is C squared plus D squared. If you take what C squared equals and fill that in, right there, you will have the formula A squared plus B squared plus D squared equals E squared. And then if you take the square root on each side, you'll get rid of the exponent of 2 on the E, and you'll have the square root of A squared plus B squared plus D squared. So that is the distance formula in 3D. Okay. It's very similar to 2D, except instead of just squaring one number and another number and adding them up, you have to square 3 numbers, add them up, and take the square root. Okay, so there's one more extra number you have to square. Okay, so there's a reminder of how you do it in 2D. The distance formula says you find the length of one side, the length of the other side, add them up and take the square root. But in 3D, we're going to have to find the length of one side, and another side, add them all up, and take the square root. And that's pretty much how a lot of the formulas are going to work today that we're going to extend from 2D to 3D. You pretty much just have to take the 2D part, and you have to add on one more section for the z's, which makes it 3D. Okay, so coordinates. You're going to have what we call an ordered triple in 3D. So x, y, and z. You could essentially think of all the formulas we've been doing up until now as having a z value of 0. So if you just remember the 3D formulas for the test, all the 3D formulas work in 2D. Just let all the 3D parts be 0. Yes?
Just like a Pythagorean theorem can work without that cosine. Wouldn't that be a 2AB? Cosine.
Yeah, on a right triangle, yep. Okay, so this formula doesn't particularly relate to a vector. It's just 2 points and finding the distance between them. But it is a 3D formula, and we're studying 3D coordinate system today, so it's a good first formula to take a look at. Yep.
I was going to say, for the side E, you shouldn't have used E because that might be Euler's number.
Yeah, so then
Probably
different letters can also stand for different things, but yeah, in the context of this problem, E would be the length of that diagonal. But yep, I know what you mean. Okay, so any question why there's 3 things added up, squared, added up, and then taking the square root? It's a double application of Pythagorean theorem. That's what it is. All right, so let's try to find the distance between those 2 points. So what I would do is set everything up first. So you got everything written down that you need for your formula, and now we'll fill it in. Okay. What am I going to fill in my first parenthesis? Yep. 4 and -1. Okay, so that's the first one. How about the second one? Yeah.
3 minus, no, it's -2 minus 3.
-2 minus 3. And the last one. 5 minus 2. Okay, and remember what you're really doing here is you are doing Pythagorean theorem twice. You are finding the length of one side, and you're using that to do Pythagorean theorem again to find the length of a different side. Okay? But it's all built into the formula. Okay, so we're going to get 5 squared. -2 minus 3 is -5 squared. Plus 3 squared. So as a exact answer, what am I going to get for this distance between those 2 points? Yeah, right?
Root 59.
Yep, square root of 59. Okay. And that's the distance between the 2 points. Just like in 2D, if you get a square root you can reduce, you need to reduce it. If you ever need to use that in a calculation and it ends up in the bottom of a fraction somehow, you need to also fix that. Question on finding the distance in 3D. All right, now let's look at some vectors in 3D. So when we write a vector in unit vector notation, that's unit vector notation in 2D. A times the unit vector I plus B times the unit vector J. I've already said it a couple times, but we're going to need one more unit vector. And what's going to be the name of the third unit vector? Yeah?
I think it was K.
K, yep. So I points in the direction of the positive x-axis. J points in the direction of the positive y-axis. Between those two vectors, I and J, you can travel anywhere you want in that area. That's like the floor of the box. With K, now we can travel up off the floor of the box. So K is going to be a unit vector that points in the positive z-axis direction. The A, the B, and the C, those are just your components. But I'm not going to say horizontal and vertical components anymore. Okay, because 3D, what does horizontal and vertical mean as much? Right. In 3D, I'll say that this is the x-axis component, the y-axis component, and the z-axis component. And those, they're just numbers. Okay, the A, the B, and the C can be positives, negatives, fractions, decimals, or a 0. And as I've said a couple times, essentially this has been 0 all week. We have not had a 3D component to any of the vectors. You can use either notation. Okay, that top one is the unit vector. The bottom one we called algebraic vector notation. In 2D, what did we call a vector that had its initial point at the origin? This last thing we did on Monday. Yep. That was called the position vector. Well, it's called exactly the same thing in 3D. If a vector has an initial point at the origin, it's called a position vector. Let's go like this. Okay, so how did we find a position vector in 2D? That was our formula. Okay, so this is the part where I'm kind of reviewing everything we did throughout the week, and now we're going to extend it to 3D. To find a position vector, you look at your initial point and your terminal point, and you subtract them. Does the order you subtract them in make a difference?
Yes.
Yes, order is important. It's terminal minus initial. So now, in 3D, instead of having just an x and a y value for the coordinate, we're going to also have a z value. So what do you think I'm going to have to add on to my position vector formula to make it work in 3D? Yeah, that's the 2D. Yep.
Z-axis component.
Okay, and what specifically are you going to put in the formula?
Between the y's and the second angle bracket, it's going to be comma z2 minus z1.
Right. So we're going to do everything we did before, and we're just going to put this extra component on the end for the z-axis. z2 minus z1. All right, so let's see if we can find the position vector between those 2 points. If they don't label which one is which, the way that I did it, how do you know which one is initial? Yeah, Ben?
Probably the first one would be 1.
Yeah, the one with the 1 is always the initial, the 2 is always the terminal. All right, so let's figure out our position vector. Set that up. I'm gonna have some calculations in there. Can somebody give me my first calculation to get the x-axis component of my vector? Yeah.
4 minus negative 1.
4 minus negative 1. Okay, how about for my y-axis component? Yep.
6 minus 0.
6 minus 2. And my z-axis component? Yep. 2 minus 3. Nice, it's like exactly what we did in 2D. We're just now doing it one more time to get 3D. So 5, 4, negative 1. Okay, that's in the algebraic notation. How about if I wanted it as a unit vector? How would we do it that way? Yeah.
It would be 5i plus 4j minus z. Or k.
Right. So 5i plus 4j minus k. This is probably the one we want to get used to using more, the unit vector. So essentially that means you're going to stack up 5 of the i's, 4 of the j's, and down 1 of the k's. But we're not going to draw that. Excuse me. Okay, so now some formulas from 2D, but we're going to extend them to 3D. Okay, so in 2D, if I wanted to add or subtract 2 vectors, that's what I would do. I would take the x-axis components and add them, take the y-axis components, add them. But what do you think I have to put now because it's 3D? Right?
Z1 plus Z2.
Right. If we're going to add them, then we also have to add a section on the end of the formula for the z-axis components. Okay, that's Z1 plus Z2. if you are subtracting vectors, well, the order matters. And if it's v minus w, then you do x1 minus x2, y1 minus y2, and if you're doing 2D, you're done. With 3D, do it one more time. z1 minus z2. Okay. A number in front of a vector. What do we call that operation? Yep.
Scale.
Scale, well, the number in front is scalar, and the whole operation is called, yeah?
Scalar vector.
They can have like a word
Oh,
that describes
an
arithmetic.
operation. Multiplication.
Scalar multiplication, yeah. So this is scalar multiplication. It's a number times a vector, which when you scale a vector, one thing that could happen is the vector does what? Well, Cole, what's one thing that can happen when you scale a vector? Dex?
Can lengthen.
Can lengthen, that's one. What's another thing that can happen? Joe?
Shorten.
Can shorten, there's two. And there's one more thing that can happen.
Flip 180 degrees.
And how would it rotate 180? When would that circumstance come up? Yeah,
The scalar is negative.
if the scalar was a negative. So scalar, I kind of made a comparison to distributive property when you do it. If you're scaling vector v, you multiply the scalar times the x component and the y component. Well, now in 3D, you're going to multiply it by the z component. So you multiply each component of your vector by the scalar. So very similar. And magnitude. Okay, we can also do magnitude in 3D. Now, if you have an idea of how to find the distance between 2 points in 3D, finding magnitude in 3D, the formula is going to look very similar. Okay, very similar. Can someone remind me of the formula to find the magnitude in 2D? And we're using vector v. So you should be referencing the vector v values. Yep.
Square root of x1 squared plus y1 squared.
Okay. So in 2D, there's the magnitude of v. x1 squared plus y1 squared. What else is there going to be there to now do it in 3D? Yeah.
Plus 1 squared.
Right. It's a double application of the Pythagorean theorem. Right? You're really finding a diagonal distance like across the bottom, and then you're using that diagonal distance with the three-dimensional height to get another diagonal. So this is really just Pythagorean theorem twice. All right, so let's try a few of those. Okay, so here's our two vectors. We've got 2i plus 3j minus 2k, and 3i minus 4j plus 5k. So let's start, let's just add here. And let's do it as a unit vector. Okay, unit vector notation. Anybody think they could tell me what you would get when you add v plus w? Yeah.
5i minus j plus 3k. Or in... are we
Yeah,
just-
that notation's good.
Okay.
Yep. So 5i minus j plus 3k. So that's what you get when you add them up. And that's the only way we're going to add them up. We're not going to do it as a visual. Okay. You can. If you're going to do it visually, it's probably easy to use like a computer where you can draw the vectors in 3D and then actually like rotate it and look at it from different perspectives. All right. The magnitude of V. All right. What's going to be my calculation to find the magnitude of V? How about Michael?
The square root of 2 squared plus 3 squared plus negative 2 squared.
Yep. So 2 squared plus 3 squared plus negative 2 squared. So that's going to give me 4 plus 9 plus 4. That gives me the square root of how much? Yep. 17. Yep. Okay. Is that answer a vector or a number? Yeah.
Number.
That's a number. When you find magnitude, you're not finding a vector. You're finding the length of a vector. Okay? It's just a number. This is a vector. Okay? So it's still important to remember what you get when you do different operations. Adding vectors, subtracting vectors, scaling vectors, all results in a new vector. Finding magnitude results in a number. All right. Well, I just said this one. Scaling is going to result in a new vector. And what would 3w be in this case? How about Moises? What would 3w be?
9i minus 12j plus 15.
Yep. So triple each component. 9i minus 12j plus 15k. There we go. Any question on that? All right. So the next thing we're going to look at is dot product. Okay, dot product in 2D. Well, we just did that yesterday. So I'm hoping we can figure out the dot product for 3D today. What do you think the formula is going to be to find the dot product between V and W there? Yeah?
Would it be x1 times y1 times z1? Or something along the lines of that? Oh.
So it's
no,
going to
wait.
follow the same pattern we did
I just
yesterday, but just
realized it would
extending
be
it one more time to the z's.
x1 times x2 plus y1 times y2 plus z1 times z2.
Yeah. So it's product of the components, all separate, or the x components, y components, z components, and then add it up. When you do the dot product, what kind of result is the answer going to be? Yeah?
Isn't it a number?
It is a number. Yep.
Because you're not taking xi, right? That you're just taking the flat x,
Yep.
y, z, but not xi, y, j.
Okay. So let's find the dot product between those two vectors. Amaya, what's going to be the first part of my calculation to get the dot product between those two?
5 times 2.
Um,
5?
Yeah, let's just write it as 2 times 5 to follow the pattern. So it's V first, then W. Okay, so 2 times 5 plus, what's going to be the next part of my calculation? Yeah.
3 times 3.
What is it?
3 times 3.
3 times 3?
Or negative 3 times?
Negative 3 times 3, yeah. So negative 3 times 3. And the last part of my dot product calculation? Yeah. 6 times -1. Okay, so that gives you 10 minus 9 minus 6. So it's going to give us -5. Okay, so that's the dot product between two vectors in 3D. And what do you think we're going to use the dot product to figure out? Yeah,
The angle.
the angle. Yep. So you can do the angle between two vectors in 3D exactly the same way we did it yesterday. So now, if you're wondering why is this formula the same? Every formula we had to modify a little bit to incorporate the 3D. Well, we've already modified this formula. This is a 3D dot product over a 3D magnitude and another 3D magnitude. So essentially that is the modified formula for 3D. It looks the same as 2D when we write it out like that. Yep.
Also, it's all numbers, so you don't have to add a third value to it.
Yeah, it's just numbers.
Taking the numbers from each one that you get.
Yep,
So,
yep, it's all numbers. There's no vectors in this formula. Number, number, number. Yep. Okay, so in 3D, when you're finding the angle between two vectors, it's just like 2D, except now your angle can come up off the board, but you're still finding that same angle between the two vectors. Now, I'm going to use the vector we already had because we already know the dot product. 2, -3, 6, and 5, 3, -1. Yep. So the dot product is -5. Okay, for magnitude of u, it's going to be what plus what plus what under the square root. Yeah?
Squared plus -3 squared plus 6 squared.
Yep. And if you square each one of those, what do you get?
Oh, you're asking me?
Yeah.
4 plus 9 plus 36.
Plus 36. Okay, add that all up. 4 plus 9 gives me 13. 13 and 36 gives me 49. That gives me a magnitude of 7 for u. And what are we going to have added up under the square root when we do the magnitude of v? Yeah.
5 squared plus 3 squared plus 4 squared.
And when you square each one of them, what will you have?
25
Yep.
plus 9 plus 1.
Yep. So 25 plus 9 plus 1, it's going to give me the square root of 35. All right, now it's pretty much the same that we did yesterday. Cosine theta equals the dot product over the product of the magnitudes. Dot product is -5. Product of the magnitudes is 7 root 35. Okay, and to get theta by itself, we need to do what? Yeah, take the inverse cosine. Okay, when you type that in, just be careful with parentheses. You do want to put the denominator in parentheses, so it does 7 root 35 altogether. Just like that. Okay, I'm going to close my denominator, and then I'm going to close my inverse cosine. So that gives me an angle between the vectors of 96.93. Put it down here. Don't forget your degree symbol. All right. So any questions on that? So that reviews a lot of what we did in 2D. Okay? This is something that we didn't do in 2D because you can't. Okay? It's called the cross product. So the cross product is a second way to multiply two vectors together. First of all, it only applies to 3D. There is no such thing as a cross product in 2D. So I just said that. There are applications to it. We're not going to get into the applications of cross product. I'm going to show you how to do a cross product. But it would have to do with like physics, geometry. One example would be like if you had a lever attached to like a pivot point and you were pulling on it and you wanted to know how much torque you were getting on the lever, you could use a cross product if you were pulling straight down to figure out how much torque is being exerted on the lever. And it's an application I've done in the past sometimes, but we're just not going to do it this time. Now, there's different ways to calculate the cross product. Unfortunately, the simplest way to calculate the cross product, you need to know some information about matrices that I don't think we know yet. Okay, you have to know about what's called determinants. So there's another way we can find the cross product. It's not the fastest way, but it doesn't require me to show you any other previous concepts. And the formula that we're going to use is called Sarris's rule. So Sarris's rule is a very specific rule for calculating the cross product between two vectors. There's really a bigger idea going on here. There's a bigger concept happening involving determinants, but we don't get into that in this class. So first of all, we are going to be using unit vector notation. V has the components A1, B1, C1, and W, A2, B2, and C2. So what we're going to do is we're going to organize everything in a matrix. Okay? To use Sarris's rule, you have to have a pretty organized problem. Okay? Laid out visually nicely. When they want you to find a cross product, you will see this symbol. You'll see an X, a small x, or a cross between the two vectors. Okay? That stands for cross product. So in 3D, I would never tell you to multiply the two vectors together, okay? Because it's not specific enough. Yeah, in 3D, I would have to say find the dot product or find the cross product. So what we're going to do is we're going to set up a matrix with 3 rows and 3 columns. And in the top row, we're just going to put an I, a J, and a K. Those do stand for the unit vectors I, J, and K. In the second row, you're going to write down the numbers that are in front of I, J, and K for V. And in the third row, you're going to write down the numbers in front of I, J, and K again for W. Just like that. So A1, B1, C1 goes in row 2. A2, B2, C2 goes in the last row. Any question on what we've set up so far? Okay. So the last thing we need to do to be able to do Sarris's rule is we need to take these 2 columns, we need to make a copy of them and put them right over on the right-hand side. Okay, so we're going to copy columns 1 and 2 to the right of the third column. So what's that going to give us? All right. So we have I, J, K, and then we're going to copy over the I and the J. We have A1, B1, C1, and then we're going to copy over A1 and B1. And we have A2, B2, C2, and we're going to copy over the A2 and the B2. So now, you should have something like that. We don't have to worry about the diagonals yet, but that's the next step. Okay, once you set that up, that's your visual that's going to help you to find the cross product. The cross product involves 6 calculations. So
And
6 calculations.
multiplication.
Yep, we're going to do some multiplication
Addition.
and some addition. Yep. So we're going to multiply some diagonals together. Okay, I've labeled them. I guess if you don't have different colors, you could use diagonals 1, 2, 3, 4, 5, 6. But I've got 3 diagonals that go down into the right, and I've got 3 that go down into the left. There's no other diagonals in that problem. A diagonal needs to include 3 rows. Right? So if you think, well, what about, is this a diagonal right there? Nope. Doesn't include 3 rows. So what we're going to do is we're going to start by multiplying together everything that's on that first red diagonal. And remember, B1 and C2 are going to be numbers. So you might have like an I, a 2, and a 5. That would be I times 2 times 5. That's 10I. Right, so multiply everything that's on red diagonal number 1. We're going to add that to the product of red diagonal 2. And then we're going to add that to the product of everything on the third red diagonal. Okay, that's the first half. Now, the second half is to subtract. You are going to subtract everything that's on blue diagonal number 1. Then you're going to subtract everything that's on blue diagonal number 2. And then you're going to subtract everything that's on blue diagonal number 3. Now, could one of these subtractions turn into addition? Yes. If you are subtracting a negative, it would turn into a positive. All right, so we'll see if that happens. Okay, so you multiply everything that goes down and to the right, and you subtract everything that goes down and to the left. And you're going to have some like terms there. Red diagonal number 1 is going to be a number with I. Blue diagonal number 2 is going to be a number with I. Okay. Red diagonal number 2 is going to be a number with J. Blue diagonal number 3 is going to be something with a J. So you're going to be able to combine those together. All right, so let's try an example of that. Okay, so let's find the cross product. And I want to do V cross W. All right, so who can tell me what am I going to do to set up my visual that's going to help me figure this out? So what's my first step to setting up my matrix? Yeah.
What did the separate?
So to put what?
Just separate the 9 and 3 from the J on that type of thing.
So yeah, let's start with that top column. Yeah, can you tell me what's going to go there? Yeah.
Do you mean the second column or the first?
I'm sorry, the top row. Top row.
All right, so wouldn't the top row after the I's and the J's and all that be
Let's start with that row.
okay, I, J, K, I, J?
So we have an I, a J, a K, an I, and a J. All right, and what's going to go in my second row?
Wouldn't that be 2, 3, 5, 2, 3?
Yep, 2, 3, 5, 2, 3. And how about my third row?
1, 2, 3.
1, 2, 3, 1, 2. Okay. So there's our visual. All right, so now, first thing we need to do is identify the diagonals that go down and to the right. Okay. So that would be this one, this one, and that one. All right. Let's multiply together everything on the diagonal that has I, 3, and 3. What's I times 3 times 3?
9i.
9i. How about j, 5, and 1? Yeah, 5j. And k, 2, 2. Yep. 4k. All right, so that's everything that goes down and to the right. Now, we're going to look at everything that goes down and to the left. And all of these get subtracted. If you end up subtracting a negative, then it could turn into addition. Okay, so we're going to minus what's k, 3, and 1 multiplied together. Yep.
3K.
So we're going to minus the 3k. Then we're going to minus I, 5, and 2.
10i.
Minus the 10i. That's where people mess up. They don't minus it. Right? You've got to minus it. And then j, 2, 3.
6j.
And we're going to minus it. Okay. Now, combine like terms, and that's the answer. What do we get when we combine our I terms together? Yep.
Negative I.
Good. Negative I. Okay. Takes care of those. How about the j's? Yep.
Minus j.
Minus j. And what about the k's?
Plus k.
Plus k. There you go. So what kind of answer is that? I minus j plus k.
Unit vector.
It's a what?
Or that's unit vector.
Well, it's unit vector notation, but this is a vector. So the
Yes.
point is, when you do a cross product, the answer that you get is a vector. It's a special vector. I'll show you why it's special in a second. Right. Let's do it one more time, except now let's do W cross V. So you're still going to have IJK, IJ. But what's going to be row 2 this time? Yeah.
1, 2, 3, 1, 2.
1, 2, 3, 1, 2. And
2,
third
3,
row?
5, 2, 3.
2, 3, 5, 2, 3. So we are checking to see, will it come out the same? That's what we want to know. So let's start with going down and to the right. J32 gives me 6J. K13,
3.
3K.
Okay.
And, oh wait, did I go off one?
Yeah, you started on.
Oh, that's okay. We're still okay.
Yep.
What's I25?
10i.
10i. That's fine, it's commutative, so it still works. So down and to the right, I add. What's important is now I subtract. K22,
4k.
subtract it. That's I33
9i. Minus 9.
minus it. And J15
Minus 5K.
minus 5J. Look at what you get. 10i minus 9i.
I.
That's just 1i. 6j minus 5j,
Plus j.
just plus a j. And 3k minus 4k,
Minus 1k.
minus 1k.
It's inverted.
Yeah, it's the opposite of the vector you got the first time. So here you had -1, -1, 1. This is 1, 1, -1. So the connection between the cross product, if you switch the order, you don't get the same answer. But the answer you do get is connected to the first one, but it points in the opposite direction. So technically, if somebody asks you to find the cross product both ways, once you find the first one, if you did it right, just change the signs, and that's the second one. Okay. So that's how you find the cross product. And we're not going to go through and do it, but what is interesting about the cross product is that if you find the angle between this vector and that one, they will be perpendicular. And if you find the angle between this vector and that one, they will also be perpendicular. So the cross product will always take two vectors and give you a third vector perpendicular to both of them. That's what the cross product does. Always. That's why it doesn't work in 2D. Because you can't do that in 2D. But in 3D, you can. All right. Any questions on it? Okay. So yeah, the application is torque on a lever, which I told you we weren't going to do. So homework is, most of it's in the book, but didn't have a cross product problem, so I just put one in. So find V cross W and W cross V. Okay, and I will be after school today, if anybody needs to stop by for extra help. Okay.